Bismillah ar-Rahman ar-Rahim. Vector x is n-dimensional. It has n components from x1 to xn. A set S in the n-dimensional real space is convex if for every x and y in the set and for every lambda from 0 to 1, the point lambda x plus 1 minus lambda y is in S. This is the set of the points on the line segment connecting x and y. For a set to be convex, if we pick 2 points in the set, connect them with a line segment, then the full line segment must be in the set. And this must be true for every pair of points in the set. This set is not convex because if I choose this as point x and this as point y, connecting x and y with a line segment, part of this line segment is outside the set. This set is not convex. Whenever we have a summation of points, each multiplied by a coefficient theta I, such that theta I is non-negative for every I, and the sum of the thetas is equal to 1, we say that we have a convex combination. A convex combination is a linear combination where the coefficients are all non-negative and their sum is equal to 1. This, of course, implies that at least one of the coefficients is strictly positive. What we have here is a convex combination of x and y. These coefficients are non-negative and their sum is equal to 1. Consider real-valued function g with a domain that is a subset of Rn. This function is convex if the domain is a convex set. Moreover, the function should satisfy the following functional inequality for every lambda in 0 and 1, and for every x and y in the domain of the function, g of lambda x plus 1 minus lambda y is less than or equal to lambda g of x plus 1 minus lambda g of y. The function is concave if the domain is a convex set, and the function satisfies the inequality that g of lambda x plus 1 minus lambda y is greater than or equal to lambda g of x plus 1 minus lambda g of y. This should be true for every x and y in the domain of the function and for every lambda in the interval from 0 to 1. The main objective in this video is to obtain an equivalent definition for a convex function in case the convex function is differentiable. It is very useful to introduce this function, which is phi of lambda. To define phi of lambda, we pick 2 points x and y in the domain of the function g. The domain is assumed to be an open set. Therefore, every point in the domain has a neighborhood that is completely in D. Phi of lambda is g of lambda x plus 1 minus lambda y. Phi also depends on x and y, but here I just emphasize the dependence on lambda. Lambda is between 0 and 1. What is the derivative of phi with respect to lambda? Function g is a function of n variables. Here we have zk is equal to lambda xk plus 1 minus lambda yk. If we want to differentiate phi with respect to lambda, then we apply the chain rule. We have a summation with n terms. We differentiate the function g partially with respect to zk. Then we need to differentiate zk with respect to lambda. If we look here, this can be written as lambda xk minus yk plus yk. The derivative with respect to lambda is xk minus yk. The first derivative of phi with respect to lambda is summation k from 1 to n, the partial derivative of g with respect to the kth component, times xk minus yk. If we collect the partial derivatives in a vector, this is the gradient vector. If we have those differences in another n-dimensional vector, we can write down the first derivative of phi with respect to lambda as the inner product of these two vectors. The first derivative of phi with respect to lambda, denoted here as phi and a superscript 1 between 2 brackets, is equal to the gradient vector transpose multiplied by this vector written here as x minus y. What about the second derivative of the function phi? The second derivative is the derivative of the first derivative. So we need to differentiate every term here. Xk minus yk does not depend on lambda, but we have this partial derivative. And the partial derivative is generally a function of z1, z2, all the way to zn. So the second derivative is summation k from 1 to n. We have xk minus yk. We need to differentiate the partial derivative, which depends on n variables. Applying the chain rule again, we have another sum with n terms. We differentiate the partial derivative with respect to zj. Then we need to differentiate zj with respect to lambda, and this gives us xj minus yj. I am assuming here that g is a C2 function. It has continuous second order partial derivatives. The double sum is equal to summation k from 1 to n, summation g from 1 to n. The second order partial derivatives multiplied by xj minus yg xk minus yk. We have a quadratic form which can be written as vector x minus y transpose vector x minus y. Between them, we have a matrix. The matrix of the second derivatives is the Hessian matrix. It's a function of z, which is lambda x plus 1 minus lambda y. Here is the Hessian matrix. In our case here, it is a symmetric matrix. What is interesting about function phi is that the function g is convex if and only if phi of lambda is convex. And when I say that phi of lambda is convex, it's convex for every x and y from the domain of function g. Phi of lambda is g of lambda x plus 1 minus lambda y. Phi is convex if and only if g is convex. This is useful because function phi depends on the scalar lambda, while function g is a function of n variables. Sometimes, to prove that a function is convex, it's much easier to deal with this function of one variable. Let's prove this statement. Assume that g of x is a convex function. X and y are from the domain of g of x. Alpha, lambda 1, lambda 2 are in the closed interval from 0 to 1. Let's investigate phi of alpha lambda 1 plus 1 minus alpha lambda 2. To show that phi is a convex function, using the definition of convexity, we need to show that it is less than or equal to alpha of phi of lambda 1 plus 1 minus alpha of phi of lambda 2. How can we show this? We start with the left-hand side. What is given is that g is a convex function. So we write function phi in terms of function g. Phi of alpha lambda 1 plus 1 minus alpha lambda 2 is g of alpha lambda 1 plus 1 minus alpha lambda 2. This scalar is multiplied by x plus 1 minus this scalar. We are writing a convex combination, 1 minus alpha lambda 1 plus 1 minus alpha lambda 2. This scalar is multiplied by y. Rewrite this one as alpha plus 1 minus alpha. This part here can be written as alpha times 1 minus lambda 1 plus 1 minus alpha times 1 minus lambda 2. We have function g. The n-dimensional vector here can be written as alpha. We have lambda 1 x. We also have 1 minus lambda 1 times y plus 1 minus alpha multiplied by lambda 2x plus 1 minus lambda 2 times y. Recall that x and y are from the domain of function g. This is a convex combination of x and y because lambda 1 is between 0 and 1. Function g is convex. Its domain is a convex set. If we choose any 2 points, x and y, any convex combination of them will also be in the domain of function g. The same applies here. X is from the domain of g, y is from the domain of g. This is a convex combination of x and y. Because g is a convex function, its domain is a convex set. Lambda 2 x plus 1 minus lambda 2 y is in the domain of function g. So this is in the domain of g. That is also in the domain of g. Alpha is between 0 and 1, and we have here 1 minus alpha. This vector here is a convex combination of these two vectors in the domain of function g. Because function g is convex, it satisfies the functional inequality. G of this convex combination is less than or equal to alpha times g of lambda 1 x plus 1 minus lambda 1 y plus 1 minus alpha g of lambda 2 x plus 1 minus lambda 2 y. This part here is phi of lambda 1, and that one is phi of lambda 2. Given that function g is convex, we conclude that function phi is also convex. We have an if and only if statement, which means that if we start with a convex function phi, then g must be a convex function. Take alpha between 0 and 1, x and y from the domain of function g. Investigate g of alpha x plus 1 minus alpha y. By definition, this is phi of alpha. To prove that g is a convex function, we need to show that this is less than or equal to alpha g of x plus 1 minus alpha g of y. How can we do this? We need to exploit the given convexity of function phi. The trick here is to rewrite this alpha as alpha times 1 plus 1 minus alpha times 0. The domain of function phi is the closed interval from 0 to 1. We have here 1 and 0. These are points in the domain of function phi. Alpha is between 0 and 1. This is a convex combination. Because function phi is assumed to be convex, this quantity here is less than or equal to alpha times phi of 1 plus 1 minus alpha times phi of 0. Phi of lambda is g of lambda x plus 1 minus lambda y. If lambda is equal to 1, we get g of x. if lambda is equal to 0, we get g of y. This inequality is true. G is convex if and only if phi is convex. Suppose that G has continuous first-order partial derivatives. We want now to show that function G is convex if and only if, for every x and y in the domain of G, g of x is greater than or equal to g of y, plus the inner product of the vector x minus y and the gradient vector of function G evaluated at y. Suppose that we have a convex function G satisfying this inequality. We want to derive this one here. Rewrite the convexity condition using function phi. This is phi of lambda less than or equal to lambda of phi of 1 plus 1 minus lambda of phi of 0. The right hand side is equal to lambda phi of 1 minus phi of 0 plus phi of 0. Move phi of 0 to the left hand side. This inequality can be rewritten as lambda times phi of 1 minus phi of 0 is greater than or equal to phi of lambda minus phi of 0. If we assume that lambda is strictly positive, we can divide both sides of the inequality by lambda. We get that phi of 1 minus phi of 0 is greater than or equal to phi of lambda minus phi of 0 over lambda, which is lambda minus 0. This inequality is true for every positive lambda. We can take the limits of both sides as lambda tends to 0 from above. The left-hand side does not depend on lambda, so the limit is phi of 1 minus phi of 0. On the right-hand side, we have the definition of the first derivative of function phi at 0. Note that because g is differentiable, then phi is differentiable. We obtain the first derivative of phi with respect to lambda as the inner product of vector x minus y and the gradient of function g at lambda x plus 1 minus lambda y. The right-hand side is the first derivative of phi evaluated at 0. We have established the inequality that phi of 1 minus phi of 0 is greater than or equal to the first derivative of phi evaluated at 0. Let's rewrite everything in terms of function g. Phi of 1 is g of x, phi of 0 is g of y, and the first derivative evaluated at 0 is the inner product of x minus y and the gradient vector of g evaluated at y. If g is convex, g of x is greater than or equal to g of y plus the inner product of x minus y and the gradient vector of g evaluated at y. This is true for every x and y in the domain of G. Since this inequality is true for every x and y in the domain of G, it is also true that g of y minus g of x is greater than or equal to the inner product of y minus x and the gradient vector evaluated at x. Add these two inequalities, we get that 0 is greater than or equal to the sum of the right-hand sides. Move the terms to the left-hand side. This one I write as the inner product of the gradient vector. Rather than having a minus sign, I put here x minus y. Then we have minus the inner product of the gradient vector at y and x minus y. This quantity is non-negative. This means that if we have any x and y in the domain of the convex function, if we have the inner product between x minus y and the gradient of the function at x minus the gradient of the function at y, this inner product is always non-negative. Now we want to show that if there is a function satisfying this inequality here for every x and y in its domain, then the function is a convex function. Consider the n-dimensional vectors x1, x2, x3 in the domain of G. Apply this inequality to x1 and x3. Apply the inequality again using x2 and x3. We get these two inequalities. We multiply the first one by lambda and the second one by 1 minus lambda. The inequalities are preserved because lambda and 1 minus lambda are non-negative. On the left-hand side, we get lambda g of x1 plus 1 minus lambda g of x2. On the right-hand side, when we sum lambda g of x3 plus 1 minus lambda g of x3, we get g of x3. We get the inner product of the gradient vector evaluated at x3. What is the other vector? It is the scalar lambda multiplied by x1 minus x3 plus the scalar 1 minus lambda multiplied by x2 minus x3. This is equal to lambda x1 plus 1 minus lambda x2. Then we have minus x3 multiplied by lambda from here and 1 minus lambda from there. This is 1. This inequality is true for every x1, x2, x3 in the domain of function G. Because function G has a domain that is a convex set, if x1 is in the domain, x2 is in the domain, any convex combination is in the domain. The point lambda x1 plus 1 minus lambda x2 is in the domain of function g. What we can do is to use x3 equal to lambda x1 plus 1 minus lambda x2. When we do this, this becomes the all-zero vector. The inequality we get is that lambda g of x1 plus 1 minus lambda g of x2 is greater than or equal to g of lambda x1 plus 1 minus lambda x2. This is the convexity condition for function g. If we have function g with a convex domain, and if this inequality is satisfied for every x and y in the domain, we get this functional inequality, thereby indicating that function g is a convex function. The next part is an investigation of the convexity of function g of x if it is twice continuously differentiable. Specifically, we want to show that function g of x with a convex domain is convex if and only if the Hessian matrix is positive semi-definite for every x in the domain of function g. Suppose that the Hessian matrix is positive semi-definite. Let's write the Taylor polynomial for function g. G of x is equal to g of y plus the inner product of vector x minus y and the gradient of function g evaluated at y plus 1/2 of this quadratic form. We have vector x minus y transpose on the left, vector x minus y on the right, and between them we have the Hessian matrix. The Hessian matrix is evaluated at a point on the line segment connecting x and y. That is, the Hessian matrix is evaluated at some convex combination of x and y, lambda x plus 1 minus lambda y. Lambda here is in the open interval from 0 to 1. It is given that the Hessian matrix is positive semi-definite for every point in the domain of function g. This quadratic form is greater than or equal to 0. Consequently, g of x is greater than or equal to g of y plus the inner product of the gradient vector evaluated at y and vector x minus y. Using the first order condition, this is equivalent to the convexity of g. If the Hessian matrix is positive semi-definite at all points in the domain, we get a convex function. We want now to prove the converse. That is, if function g is convex, the Hessian matrix is positive semi-definite. Let's think about this in one dimension. On the previous page, we proved that if g is a convex function, then we have this inequality. And this inequality was used to prove that the inner product of x minus y and the gradient at x minus the gradient at y, this inner product is greater than or equal to 0. If big N is equal to 1, we have a function of one variable. This inequality can be written as the derivative of the function at x minus the derivative of the function at y times x minus y is non-negative. Suppose that x is not equal to y. Divide both sides of the inequality by x minus y squared, which is strictly positive. We get that the derivative of function g at x minus the derivative at y over x minus y, this ratio is non-negative. Take the limit of both sides as y tends to x, we get 0 on the right hand side. What we have on the left hand side is the definition of the first derivative of the first derivative. We get the second derivative of function g evaluated at x. This argument is good if g is a function of one variable. Starting from the convexity of g, we have proved that the second derivative is greater than or equal to 0. How can we extend this to the general case and show that the Hessian matrix, the matrix of the second order partial derivatives, is positive semi-definite? The trick here is to use function phi, which is a function of the scalar lambda. We have proved that g of x is convex if and only if phi of lambda is convex. If g is convex, phi is a convex function. And by this argument here, phi, which is a function of one variable, because it's convex, its second derivative with respect to lambda is non-negative. What is the second derivative of function phi expressed in terms of function g? The second derivative is a quadratic form. We have x minus y transpose x minus y. Between them, we have the Hessian matrix evaluated at lambda x plus 1 minus lambda y. For every x and y in the domain of function g, this quadratic form is greater than or equal to 0. Pick point z in the domain of the function g. Consider arbitrary vector v. The 2 points or the 2 vectors z plus tv and z minus tv are in the domain D. If t is small enough, we are assuming that the domain D is an open set. For any point in D, there is a neighborhood that is completely inside D. So if I have the point z and I add tv or I subtract tv, there is a sufficiently small positive value for t such that these 2 points are guaranteed to also be in the domain of function g. We set x equal to z plus tv and y equal to z minus tv. The conclusion that we have here is valid for every x and y in the domain and for every lambda. The inequality is valid for the special case when lambda is equal to 1/2. X minus y is equal to 2tv. Lambda x plus 1 minus lambda y is equal to 1/2 x plus 1/2 y. This is 1/2 of 2z. This is z. The inequality is 2t, which is a scalar, v transpose, the Hessian matrix evaluated at z. Then we have the scalar 2t multiplied by v. We have the scalar 4t squared and the quadratic form v transpose, the Hessian matrix at z times v. This is greater than or equal to 0. We started with convex function g. Because it is convex, then the function phi is a convex function, and we have proved that functions of one variable, if they are convex, then the second derivative is non-negative. The second derivative of phi is this quadratic form. What we have here is true for every lambda between 0 and 1, and for every x and y in the domain. We did particular choices. We set lambda equal to 1/2, and we set x and y equal to z plus or minus tv. V is an arbitrary vector. Z is a vector in the domain of function g. T is a positive real number because the domain D is an open set. If T is small enough, then Z plus or minus TV will also be in the domain. Making these choices for lambda, x, and y, we obtained that 4t squared times this quadratic form is non-negative. If we divide both sides by 4t squared, we get that V transpose h of Z V is greater than or equal to 0. This is true for every Z in the domain and for every arbitrary vector V. This is exactly the definition of a positive semi-definite matrix. Our conclusion is that if function g is a convex function, the Hessian matrix is positive semi-definite at any point in the domain of function g.